Is it going? Okay, it is. Okay, so we're going to be looking today at the start of Module 6. This is going to be divided into two main parts. It's going to be Chapter 11, but we're covering belt and chain drives. Today, we're going to focus on belts. The next time we get together, we will focus on chains. So let's take a peek kind of at the learning plan and what's out here. So first and foremost, you're going to notice we have a PowerPoint presentation here for Chapter 11, so we'll be focusing on that. And then you will see that you also have practice problems to hand in, and those are going to coincide to the examples in the book here. So we're going to be doing two of these examples tonight, 11.1 and 11.2. And then the next time we get together, we will do 11.3, which is going to be the gears. Additionally, you have three, if you would, questions to answer. The first one is kind of, I guess my standard is, what did you learn? Okay, kind of, think about what we covered after we've gone over the practice problems and gone through the lecture. Write a couple things that you've learned. And then I want you to name and describe one place where you see an application of belt drives and one place where you see an application of chain drives. I'm going to tell you, you cannot put a bike. All right. You can't put a bike for chain drive. That's off the table. All right. You got to look somewhere else. There's plenty of them around. So that's kind of an easy peasy gimme. So I'm not gonna allow that one. So that's practice problems. And then you're going to notice that for assignment 6, at the end of the chapter, you have 8 problems that you're going to be doing. The first 4 tonight, we will be covering that information. And then the last 4 are going to be when we meet on Wednesday. So the first 4 are going to be belt drives. The last 4 are going to be chain drives. So I am going to go into our learning plan and I am going to pull up our PowerPoint presentation, and I have my book open. So we're ready to start. So chapter 11, belts and chain drives. So the objectives here are really to look at belt and chain drives and identify advantages, applications, and then ultimately be able to size them and specify them for an application that's described, in our problems. Okay. So first of all, belt drives are going to be used to, belt and chain drives are going to be used to transfer motion and power between rotating shafts, okay? Belt and chain drives offer the flexibility of efficient operation at large and small center distances, okay? Gears become impractical when we have distances that need to span a wide distance. That's where looking at chains and belts makes sense. So we're going to look at this in just a second, but I want to go underneath our camera. And when we talk about spanning distances and being flexible with center distance, this is just a side view of what would be a belt drive. A belt drive is always going to go over the top or go around sheaves, or sometimes we call these pulleys. Pulleys or sheaves are really what we refer to them as. You'll notice that we have an input, which is going to be the smaller one, and we have an output, which is going to be the larger one. So typically the smaller one is coming off of our motor, our engine, whatever we're going to be, if you would, driving. So it's considered what we call the driver of the machine. The driven side or the output side then is going to be the larger pulley or sheave that we see here. Okay. Now, the difference between this, or a major difference as we look at it between this and gears, is that gears have to be like right next to each other so that they engage. Okay. Chain and belt drives have this ability to span larger center distances. So when we have to achieve that, that's when a better situation or a better selection is going to be a belt or a chain drive. So again, we're going to be focusing on belt drives to start here, and then chain drives will come the last half here. All right. So let's just talk a little bit about bicycle chain drive, and this is why I'm not going to allow it for your application. So when we look at a bicycle chain drive, and I like kind of talking about this in terms of these more flexible drives, because we've all probably have firsthand experience with this application. Gosh, I look in the room here and it's so sad to me that not one person is looking up at the board or paying attention to me, I feel like. Are you guys ready? I don't know about, I can't see you guys, but and then when I get questions asked of things that I say, it is hard for me to answer without being like sarcastic. Okay. All right. Can I have everybody's attention? Thank you. Thank you. So a bicycle chain drive. A chain drive mechanism is going to transfer, like we said, motion and forces. Although in kinematics, we're not worried about forces, we are going to kind of talk about them a little bit in our examples, just because I think it's important for you to realize that we aren't completing the design here. We're laying it out, okay? So we're kind of taking that first stab at the early stages of the design process with the kinematics that we're doing. So we're going to be selecting the size of the teeth on a chain drive. We're going to be selecting the size of the belt on a belt drive. We're going to be determining, okay, what do we believe a good first iteration, if you would, of the size of the pulleys that we can get commercially. And I also want to always emphasize that we don't want to get too attached to those, because the design process is not a straight line process. Typically, what we do is we start out with a set of assumptions, and then we take a stab at what we believe is going to be the best first steps, okay? Many times in the design process, and this is something that is important to understand, is that just because we chose a belt size at the beginning, or we chose the size of a chain drive that we started with, we might have to go back and redesign it once we get to the end and we realize, oh, our stresses are too high. Oh, it's not going to work for us because the space that we have isn't what we thought it was going to be. There are millions of things that can come into play variable-wise that can change the outcome of where you think you're going. So something when you're doing a design, always be open and embrace having to maybe step back a couple steps before going forward. Okay. And that's kind of the fun part of the design process, because if you go through a design process and you don't have to go back and make any changes, or you don't have to go back and do any iterations, and you got it all right the first time, it's going to be kind of boring and it's time to move on. Do you know what I mean? Did you ever feel that way? Like when you kind of got it? I remember being at a couple jobs that I had. I knew it was time to go when I was anticipating problems, and all of a sudden it was going pretty darn smooth by the time I was releasing stuff. Okay. Then you know that you've kind of grown out of your situation, and then you want to move on and maybe explore some other challenges. That's kind of what we end up having here. Design process is always going to be, number one, there's going to be more than one way of doing it. And number two, it's not always going to go in a straight line, meaning step one, step two, step three. You might go step one, step two, back to step one for a little bit, go ahead to two and three, then go back again to two. And it's just kind of a back and forth until you get to the refined design. Okay. Anyway, so when we're transferring motion and forces and torques, even though we're not going to be dealing with forces and torques, motion is going to be our biggest deal here. So velocity ratios, just like when we were doing gear ratios, we're going to see very similar equations come up. When we're talking about belt drives, teeth don't come into play, but rotational speeds, diameters, those types of things are going to be values that we're going to be dealing with. Now, on bicycle chain drives, if you recall how they operate, up by your handlebars, you're going to have the ability to change your gears, if you would, and change, how things run by just moving a lever. And that lever then is going to push the chain onto different sprockets to get the ratios that you desire for whatever situation you might be in. It becomes a very easy way of manipulating how you're going to change your ratios. When you have gears, it's a lot harder to do that. Okay. Chain drives is another reason that belt and chain drives become a little bit more flexible, because they're easier to make changes on the fly as opposed to in like a gearbox. So they're considered what we call flexible connectors, not only in the center distance that we can change, but also in changing from one velocity ratio to another. So we're going to talk, like I said, about belts first. So if we look at starting on section 11.2, which is on page 302, the function of belts is to basically transfer rotational motion and torque from one shaft to another. The advantages that they have are, number one, they're going to have smooth operations. The nature of belts and how and the materials that they're made out of make them a quiet, smooth type of a drive, okay? They're flexible on their center distance, as we said. They are going to be low cost. Belt drives and chain drives are going to be a purchased part for most every application because unless you're working for a V-belt manufacturer, it's not something that you can readily just make or machine up, okay? So they're going to be machine elements that you're going to incorporate into your designs that you're going to purchase. They also have an advantage because they don't need lubrication. Belt drives, they aren't going to need any oil or any type of coolant to keep them cool like chains and gears will need. Chains and gears are metal on metal, so there's going to be some noise there as well as the need for lubrication so that you don't have undue wear prematurely. They're also easy to assemble and install for the most part. It's just a matter of getting the belt over the shivs, and you can design in ways of doing that. They have almost no maintenance except changing out the belt when it appears to be old. So when you start seeing cracks or wear or frays, it's time to change out that belt. And the other thing that they do is they absorb shocks more readily than the other two types of drives, meaning that they have that ability to flex or to stretch a little bit if they're overloaded. Now, materials and types. If we look at the top of page 303, we're going to notice that there are, it looks like 5 different types of belts. First, you can have a flat belt, which would really go over kind of like a conveyor, type of a situation, like a roller. But the ones that we're going to be looking at are going to be the V-belt type. And that's going to be the most popular in like machine design, if you would, or industrial machine design. Variations on that V-belt, we can see multi-V-belt. And how a V-belt works is you'll notice that we have the sides that are coming down and the bottom. Those are going to ride inside of the very same shape type of profile on what we call a shiv or a pulley. And we're going to just briefly go down to the bottom here at the bottom of that column. And you're going to notice here that this is a cross section of a V-belt shiv. The V-belt part will fit into this top portion right here. The bore that goes through would be on a rotating shaft, okay? And then there would be a keyway here as well so that it rotates at the same RPM as a shaft. But that belt is going to fit down in this profile. And so when we specify, for instance, and I'm going to go over here, the size of our belt. So the cross-sectional size here comes in 3 very popular standard sizes. There are variations on this, but a 3V, a 5V, and an 8V. And you can kind of see as the number goes up, the profile or the section gets larger. But this profile that is on your V belt has to match the profile of the belt that you specify. Okay. And as you can imagine, as we start getting larger, chunkier belts, we can push more horsepower and torque through those. Okay. And we'll talk about how you specify and how you choose where you start with that. So those are going to be V-belts. By having multiple V-belts, we just have more surface area that it allows us to then transmit more torque and horsepower through. Another type of a V-belt is going to be the cogged belt. The cogged belt is cogged, and we can see kind of these recesses on the backside, those rounded recesses. And that is just so that the belts, because they're thicker and chunkier, they help them make a radius around a V-belt, or I'm sorry, around a shiv. Okay. So that's the purpose of these little indents. But if we have a timing belt, the timing belt is a little bit different because these actually have grooves in them that are going to fit down inside of a pulley where it has actual teeth on it, if you would. So they're a lower profile, if you would, than a gear or a chain, but they have, if you would, more positive type of engagement because they're going to be on toothed pulleys. Okay. So these are going to be used a lot in automation equipment where you have to place things or time things out. And then the V-belts are going to be in situations where we may want to actually have it slip if we get into an overload situation. So it slips on the belt before it damages downstream equipment. Does that make sense? Okay. So So those are kind of some of the types of V-belts that we would be looking at. Okay. Materials, rubberized fabric, rubberized cord, reinforced plastic, leather, fabric can all be used for different types of belts. And then all of them, whether they're individually or if they're in conjunction and they have a couple different types that are there, it's all going to depend on the strength. So when we have rubberized and corded, that's going to refer to, if we look here at this cross section on the inside, we've got a couple different layers of the belt itself, but then these little circles, that's really going to be like steel wire that's going to go through there, and that adds strength to the belt as well, so it doesn't pull apart very easily. Yeah, so that's kind of the nature of the belts. Now, shivs are going to be the wheels that are connected to the shafts that carry the belt. So we already looked at that picture at the bottom of the column of a cross section of a belt. Now, they're going to be classified by their pitch diameter, and there's also certain commercially available shivs. So if we go back into our book, we go down here, you're going to notice that as we look, there is a pitch diameter on a shiv. That pitch diameter is really kind of like a gear tooth, where we had the pitch diameter on a gear tooth. It wasn't the top of the tooth. It wasn't the bottom of the tooth. It was kind of like in between. And we said that was the effective diameter. It's really the same type of thing here with belts, but it's going to be where the strongest portion of the belt is. So if we look back up here, and we see where we have these little circles, which would identify where they have like wire or cording going through them that is metal to create strength. That is going to be the strongest part of our belt, which is going to correspond to where the pitch diameter is on our shiv. Okay. All right. As far as commercially available shivs, so again, this is called a shiv where our belt is going to be going on, or a pulley. Pulley or shivs are really the same thing. The table 11.1 is commercially available shivs. So they don't make every single size, just like gears. We didn't have gears that had, every single size tooth on them, right? We had to work with whatever was considered standard or what a vendor would actually have commercially available. Same thing for belts. Okay. So as we look here, you're going to notice you have 2.2, 2.3, but then it goes to 2.5, 2.6, 2.8, and so on. So when we pick our size of our belt, these are the ones that are available to us to use for our pitch diameters. Okay. You can't just, randomly pick, because you want to pick something that's going to be off the shelf. Now, vendors are going to have the standards, but then they're probably going to have some versions of, okay? So Gates, for instance, they don't just have 3 belt sizes. These are kind of the 3 most popular. They're going to have probably 12 different types of belts, okay? And then within those different types, they're going to then be for certain applications or for certain industries. And then inside of each one of those, they're going to have their list. If they're offering, which they will, a 3V, a 5V, and an 8V, these will be in their, selection, but they might have more, and they probably will have more types of belts as well. Okay. So when we're doing our problems, we're going to be looking to this table for picking out the shivs that would be appropriate for an application. V-belt selection chart. As we turn the page and we look at figure 11.4. The application itself is going to dictate which size belt we're going to pick. So is it going to be a 3V, a 5V, or an 8V? We saw, pictorially how they change in size. So we go up in size as we go to the right here. But where do we start? So to pick the correct belt size, we are going to use the horsepower, and then we are going to correspond it to the RPMs of the faster shiv. So if we look down here, as we had peeked earlier, where we have our input and our output shiv. So one is going to be the driver, smaller one, and the driven is going to be the larger one. So we're going to look at the faster moving shaft in the application, which most often is going to be coming off of your motor, coming off of your engine. And that's going to be the RPM that we would read on the left-hand column. That gets us basically where are we going to start with the size? Okay, so we don't just pull it out of the air and just try something. We're going to use this chart to help us get us in the ballpark to, start at a good place. Okay. Sketch of the belt drive geometry. So we did look at this already. So let's look back at the bottom of page 304. And here's where we have kind of just that basic geometry. So we've got the sheave that's coming off of our driver, the smaller sheave, and then the sheave that would be going to our driven machine. Okay. Over on the left-hand side, we see W1. That's going to be the angular velocity of the shaft for that driver. So that's going to be, again, coming off of our motor, 1750 RPM, 3500 RPM, 900 RPM, whatever it might be, whatever it's rated at. We would also get a horsepower rating off of our motor as well. So again, this is what our belt size is going to be based off of, okay? Then you're going to notice that we have a center distance between where our output is going to be, and then we have a larger sheave over there. Notice that the direction of our input, our driver, and the output, our driven machine, they're going in the same direction. So gears, if you recall, when we would have two that would be engaged, they would always be going in opposite directions, right? Because those teeth would push past each other. And if our input was going clockwise, our output would go counterclockwise. In this case, our input and our output go in the same direction based on this kind of standard arrangement, okay? If you want them to go opposite, you have the option of crossing the belt over here, and now you can get them going opposite direction if you want your input to go opposite the output. Okay, that is an option for you. So, so it's not that you can't do it, but you would. It's not the most popular application, but it is achievable. Okay. Well, it could, yeah, it could rub it on itself if you don't have it offset properly. Absolutely, yeah. The other thing that you're going to notice here is that we have these angles. Okay, theta 1 and theta 2. That's what we call the angle of wrap that the belt has on each one of the sheaves. The sheave doesn't have belt around 100%. So in this case, you're going to notice that it has a little bit more-ish or right around 180 degrees. Okay, and it's going to be plus or minus. So that's all the wrap that we get on either side. And so it has to be enough friction, enough contact in order to be able to, number one, transmit the motion, but also number two, to transmit any torques and forces and horsepower that we have. Okay. All right. Center distance. We already talked about center distances. Small center distance can cause fatigue, but too large of center distance can cause the belt to whip or excessive vibrations. Okay. So the normal center distance range is going to be the equation that we see down here, which happens to be in the next column. There isn't an equation number listed for that. So if we look, here is our illustration. If we go to the next column, you'll notice that our center distance, which is right in the between here, it needs to be greater than whatever the diameter of the output sheave is. So when we look here, D2 is going to be on our output side here. So that means it has to be larger than whatever this diameter is on the right-hand side. And then it has to be less than, because we don't want it to get too long, it has to be less than 3 times adding the input and the output sheaves together, their diameters. Okay. So, so it's not a small range, but we don't want to go crazy wide either, because if these get too far apart, you could have vibration, inducing vibration, or it actually kind of, the belt would actually whip around, and we don't want that, because then it could come off of the sheaves and it'd be unsafe. Okay. And prematurely wear and probably fatigue and break. Belt length. Okay, let's look at L for belt length. Belt length, as we look at this belt arrangement here on this V-belt drive, the belt length is going to be the total distance all the way around. So if I would take a tape measure, for instance, and I would wrap it around and go all the way back, the total length would be the length of that belt. These are continuous belts. There is no break in them where you take it apart, put it over the shivs, and then click it back together. That's not how this works, okay? This is just a continuous belt. And so we have to know what the total length is, all right? And then we have to, when we design, we have to have the ability to move, for instance, the driver or the driven in and out so that we can move it in, put the belt over the top, and then move it back out to snug it up so that it can be in its normal operating, situation. We also have to accommodate for stretching of that belt. Okay. Now it's not part of this class in kinematics, but when you do machine design elements, you are going to be picking belts and shivs out of a catalog for an actual vendor. And then you're going to be specifying not only what we call the take up, but also, where you have to push it in so that you have enough to get the belt over the top. Okay. So those are going to be design design elements that you have to build in. Now, to determine the overall length of your belt, this is the equation for it, but we have to know our center distance. Okay. Now our center distance is going to be the equation we see here. So we will be using these equations when we start looking at some examples. So I'm not going to go into too much detail about them just yet because we will see them in application very soon. Velocity ratio. Okay, velocity ratio. That sounds familiar to us. We talked about velocity ratio. We go to our next page, 305, right underneath belt drive kinematics. We have VR, velocity ratio, just like we did for gears. And you'll notice here that they're comparing the angular velocity of the driver, the higher speed shaft, which is going to be the smaller shiv, divided by the lower speed shaft or the driven angular velocity. Okay. And that's just going to be that ratio. We want to know, okay, how many times is that driver going to go around to get the driven to go around once? Okay. Now, additionally, other ways that we can do our velocity ratio are here in equation 11.7. So not only is it the angular velocities of the two shivs, but we can take their radiuses or their diameters. And most often we use the diameters because that's usually something that we're, basing our design off of are those diameters. So we'll be referencing back to the velocity ratios here as well. Notice that we don't have counting the number of teeth because there aren't teeth on these V-belt drives. Okay. So we can't determine a velocity ratio there, but we can look at the physical size diameter wise or the rotational speed, and we can get the velocity ratio. Now, it does say here that belts transfer maximum power when they're speeds of 4,000 to 5,000 feet per minute. Now, what that equates to is, if we look at, I'm going to turn the page here, and we're going to look at the very top of page 306. This is a familiar equation to us. I'm going to zoom in here so that we can all see it. This is what we call belt speed. Or if you remember, we had pitch line velocity, VT, and that is the straight line velocity as the gear rotated. This is belt speed, the pitch line speed or the straight line velocity component as the shiv rotates. Okay, so if we look at an application, for instance, of a shiv, okay, here's our shiv, and here's our center. Okay. And let's say this is rotating, the shiv is rotating in a clockwise direction. Okay. And we have a belt, on there, and we're just going to not worry about where it's going to, but the belt is rotating around. Okay. So if I want to know how fast that belt is going straight line, what am I going to do? I'm going to find the radius of rotation, right? And this is going to be the straight line velocity component, but instead of calling this VT, we're calling it VB. It's the belt straight line velocity. Okay. So this is going to be our radius of rotation, which is going to be the radius of the shiv. And then they're going to be corresponded through that angular velocity to the straight line velocity component of the motion. Okay, so belt speed is going to be VB. Now, if we look here, the same equation that we've been using applies. We're going to take the radius of the sheave, which is going to be R1, multiplied by the angular velocity of that same sheave. So we have W1. So in this case, R1 refers to the radius of the driver, and W1 refers to the angular velocity of the driver. Okay. Now, in this equation, so that we can get it in the proper units, we have to convert our angular velocity W from revolutions per minute, or RPMs, to radians per second or radians per minute. We'll kind of look ahead and see which makes the most sense. Okay. And then you'll notice that in this book, there is a typo. So make sure that your R is 1 and your W is 1. They have to be matched together. You wouldn't take the radius from one and the angular velocity from the other sheave. Okay, they have to be together. So here we can also say it's the radius of the output sheave multiplied by the angular velocity of that same sheave. So this would be R2 and W2. Okay. All right. Let me go back over to our PowerPoint presentation. So again, the V, the belt speed, we want to try to target between 4,000 and 5,000 feet per minute, not inches per second, feet per minute. That's the most often used units for belt or conveyor speeds, is feet per minute. So let's look at our first example here, using some of these relationships and these equations. So I'm going to go to just on page 306 here. This is example 11.1. Now, we don't have an illustration here. We don't have an illustration, but we have a description. So let's kind of look at what we have here. It says we have a belt drive. It's used to transmit power from an electric motor to a compressor for a refrigerated truck. The compressor must still operate when the truck is parked and the engine is not running. So there's a 10 horsepower electric motor that is rated at 3550 RPM, and it has a motor sheave coming off of it at a diameter of 5 inches. The compressor sheave has a 7.5-inch diameter, and they want us to determine the appropriate industrial belt size, the operating speed of the compressor, and the belt speed. Okay, so if we look at this in terms of figure 11.5, okay, this would be the motor. Okay, the small one would be the motor. And then over here would be our compressor. Okay, so we would just imagine kind of a standard layout here where we have them in line with one another, if you would, horizontally or vertically, however they would be oriented. But then we would have our small sheave on our motor and our large sheave going to be going to the compressor. Okay, and then it's asking us to determine the size of the belt and how fast this one is rotating over here. Okay, based on the diameters that we have. So let's look at this example. Okay, let's look at this example. So this is our first, if you would, practice problem that we'll be looking at, that you'll be handing in. So this is example 11.1. I'm going to kind of go underneath here. Okay. Okay. So what we are given, it's telling us that we have a 10 horsepower electric motor rated at 3550 RPM. So our W1 is going to be our input, which is our motor, is going to be 3550 RPM. Okay. And that motor, okay, has a horsepower of 10 horsepower. Okay. So this is the motor RPM, motor rotational speed, and it's rated at a 10 horsepower. Okay. Now on that motor, there is a sheave. Okay. And it is 5 inches. So our D1 is a 5-inch diameter sheave. Okay, that's the pitch diameter of it. All right. So again, if we go back a page and we look at this, this is rotating at 3550 RPMs, and the sheave that's on here is 5 inches in diameter. Okay, pitch diameter. So just to give you a visual. So then the compressor is going to be our output. Okay, so it says the compressor sheave is 7.5 inches in diameter. So that would be our D2 is 7.5 inches. Okay, so it's a little bit bigger. They want us to find, okay, given that information, they want us to find the belt size. Okay, belt size. They also want us to find the operating speed of the compressor. That's going to be our output angular velocity, our W2. And then they want us to find that belt speed, VB. Okay. Right. Now, the first thing we're going to look at is what is the belt size? All right. The belt size is going to be based on the horsepower and the speed of that motor. Okay. And we are going to use these two values on figure 11.4. This is where it tells us what size would be appropriate for this application. So we have a 10 horsepower motor, and it is running at 3550 RPM. So it's way up here. So up here-ish is where we would find an intersection, right? So as we look here, this is in the 3V belt size, right? So that means that's going to be the belt size that would be appropriate for this application. So we can say belt size equals 3V, and this is from figure 11.4, okay? And it's utilizing that motor RPM and, I'm sorry, yeah, the motor RPM and the horsepower, right? So that means that that's going to be the size that would be appropriate. Okay. Now they already have the diameters of the sheaves done. Okay. So we don't have to go and pick out any sheave diameters, but we've got the belt size done. But now we want to know what is the rotational speed of our compressor or the output. So step number 2 is going to be finding that W2. Okay. So we're going to use the velocity ratio equations, okay, or options here. So you will notice that we can calculate our velocity ratio if we know our angular velocity of the input and the output, and we can set that equal to the diameters, right? The physical size of the diameters. We know D1 and D2, and we know W1. So we can say that W1 over W2 is going to be equal to D2 over D1. Make sure you have the right numbers where they're supposed to go, because the larger number will always go on top, because our angular velocity of our input will be a larger value than the angular velocity of our output. It'll be on the top in this equation. But physical size or number of teeth, 2's always go on top because they're bigger, okay, physically bigger. Now, we know each one of these diameters, as we said, and we know W1. So by setting these equal to each other, we can solve for W2. So if we rearrange this and we solve for W2, what do we get? W2 is going to be equal to, well, I'm not worried about the number yet. We just have to rearrange first. I want to make sure that we get that. So we're going to put this up and this down. So that means that W1 is going to be on top times D1, right? Divided by D2. Did I get that right? Did I do that right? Yeah, I think so. So now we're going to put our numbers in. So make sure you show this in variable form. I'm still taking points off. You guys have had me for statics. This is second year. I take off like 3 points if you don't show me the equation in variable form. I don't care if everything is right. I don't care. Show me the equation in variable form. That is required. Don't do anything. Don't put any numbers in. I don't care about numbers or a final answer. If I don't see that equation in variable form, it's -3 right off the top. Okay. So make sure that you're putting the equation in variable form. Then you put your numbers in. So this is going to be equal to, if we look up here, 3550 RPMs for W1 times D1, which is 5 inches, divided by D2, which is 7.5 inches. Now, you need to have your units in every phase of the problem. Points come off here too if you don't do that. And then you need to cancel out what cancels top to bottom. And then you got to look what didn't cancel. I have RPMs here. Are RPMs appropriate for an angular velocity? Yes. Okay. So that means I probably have this set up correctly. So if I take 3550 times 5 divided by 7.5, Josh, what did you get? And that's going to be RPMs, right? Did anybody else get that same number? Then you put a box around it. The other thing is, make sure that you label your variable with the value that you got. Do not put a box around a number, just 2366.67 RPMs. I want to know what that is. You have to label W2 is equal to. Also put your box around. If you don't put your box around, I don't know where your final answer is. Okay, points off. I know I am a little picky on this stuff. Oopsie chat. Okay, good. Yes, thank you. Wrong way. I want to put this over here. I know I am picky on the work that you guys do, but I'm going to say something. And I'm going to tell you, I'm going to justify myself being very picky on this. And that's why I go over practice problems. I'm showing you the format. And the reason I'm picky on this is because you guys don't take one test in this class. You get more homework problems, and I am going to be insistent on formatting and how you do it, and then I can read it. And if not, then I'm taking points off. Okay. So pay attention to the details. They're important. It's just like when you go out in industry, you're going to have a boss who's going to want you to do things a certain way. Okay. They're going to want you to dimension a certain way. They're going to want you to save parts a certain way. They're going to have part numbers. And it might not make any sense to you, but it doesn't matter. It doesn't matter. So it might not, you might be like, why should I do that? It's because Kelly wants it that way. And if you want to maximize your points on an assignment, write it out the way that we're doing it. And that's why I go over this stuff in the practice problem so that there's no secrets or there's no wondering what she wants. Okay. So make sure that you do that. I feel preachy tonight. Sorry. I don't mean to be. All right. And then the last part, we need to find the belt speed, right? So we got W2 here. Now we need to find the belt speed. Now the belt speed, whether we are using the driver side or the driven side, it's going to be the same. Okay. And we always want to try to use information that is the least calculated, meaning if we can use original information, that's what we wanted to use. So if we look at belt speed here, we want to find VB. That's going to be our part 3 here. Belt speed is going to be equal to, and the equation for belt speed is at the top of page 306. Okay. It's going to be the radius multiplied by the angular velocity. Now, remember, we want to try to get this into distance over time. So this is the equation. This is the relationship where our angular velocity has to be in radians per unit of time. So our base equation here is going to be D1. Now we're going to use D1 because we're given it as original information, and the angular velocity of the driver was also given to us. I'm pretty confident in the angular velocity of our driven or our compressor, but it was a calculated value. So it's better to stick with given information. Okay. Now, as we said earlier, we are expecting our pitch line speed to be in feet. Not feet. I'm not going to write that out. Feet per minute. Okay. Feet per minute. That's kind of the standard units. So our diameter is probably going to be in inches. So we can do the conversion to feet in the end. But what it means is for our angular velocity, we want to put this in radians per minute rather than radians per second, because otherwise we're going to end up converting it back into minutes later on, okay? So just so you know, because we're dealing with belt speed, feet per minute are the standard units. So we're going to put this in radians per minute rather than radians per second, okay? So now we're ready to put in whatever we need to. So for our diameter, we know that our diameter up here is 0.5 or 5 inches, not 0.5, 5 inches divided by 2. And then our W1, we need to convert this to radians per minute. What I'm going to do is I'm going to do it right in the problem here. So 3550 revolutions per minute. So this is going to be 3550 revolutions per minute. Okay. And I'm going to convert this right here. So I'm going to have 1 revolution, 2 pi radians. Okay. And that way I multiply across the top, divide by the bottom, revolutions cancel. And now I'm in radians per minute, and I'm going to leave it there. Okay. So that means that my pitch line speed is going to be what? What you get for a value here? James, what is the number? What is the number that you said? What 5 times 3550 times 2 times pi divided by 2. So 46.9, and that's inches per minute. So I just want to be sure. Did anybody else get that number? A little bit different number. I don't know, Chris. Did anybody else get 46 inches per minute? I don't get that. I get 55,763. Yeah.
Oh, yeah.
Okay. I'm going to say 763. Okay. And that's going to be inches per minute. This is in inches per minute. This is in inches. And then we want to end up with feet per minute. So now we're going to do a conversion of our inches to feet. So we know that there's 12 inches in 1 foot. Okay, inches cancel. So then now we're going to divide that by 12. So our final answer for our belt speed is going to be the 46.47 feet per minute. Good. Okay. Now, when you do your problems, there is a final answer key. Make sure you check the final answer key for what the units are. If you leave this in inches per minute, inches per second, and the final answer is given to you in feet per minute, you will get points off. I don't care if you say, oh, it's the same thing. Pay attention to the units, okay? Take a look at the final answers. Because again, for belt speed, feet per minute is the standard, okay? All right, so if we look back up here, that was our last variable that we needed to. So our belt size, 3V, our angular velocity of our output or our compressor, 2367 RPMs. And then our belt speed is 4647 feet per minute. Now, as we look at the 4647 feet per minute, does this compare to something like if we look at this, the maximum power, as it said earlier, there was a range. Do you remember what that range was for belt speed? 4 to 5,000, exactly. Yeah, Isaac, Jack, thank you. So this falls within that range that was given between about 4 to 5,000 is where you want your belt speed to be, and that's feet per minute. Okay, excellent. All right, so that's our first example. Let's take a look at our second example, which is going to be 11.2. 11.2. So right below that, here's another example that we're going to be looking at. And the illustration, they do have a picture of this one on the next page at the top of the page. We'll look at it in just a bit. It says we have a belt drive is required to reduce the speed of an electric motor for a grinding wheel as shown. So up here is our illustration. So this is going to be our driver. This is the motor. And up here is the grinding wheel. This is going to be our output or our driven machine. We have a 50 horsepower electric motor is rated at 1725 RPM and a grinding wheel that they want the speed up here to be reduced to about 600 RPMs. They want us to determine the appropriate belt size and find the suitable sheave sizes of stock pulleys listed in table 11.1. Also select the suitable belt length and calculate the corresponding center distance. So what I want you to do is I want you to take that statement and identify the elements that are given and the elements that we are going to try to find, okay? So if we look here, I want you to take a minute. So this is example 11.2, okay? And I want you to list the things that are given and then list the things that we need to find, okay? From what we have here. So as we look at our application and we look at the driver, do we know anything about the driver from the problem statement? What do we know, James? We know the horsepower of the motor. Okay, so motor equals how many horsepower? 50 horsepower. Okay. Do we know anything else about the motor? We do know the angular velocity. What is it?
1,725 RPM.
Perfect. And is this W1 or W2?
W1.
This is going to be W1. This is our driver, right? So this is going to be W1, right? Okay. That means that the driven up here is going to be our W2, right? Okay. What else do we know?
W2. Angular velocity.
W2, that's going to be the
600 RPM.
Now it says approximately. So I'm going to do like a little wavy line here. And this is approximately what we want that to be. And that's going to be dependent on the shivs that we're able to pick off of the standard commercial list. Okay. So it might not be exactly 600, but it says approximately 600. Okay. Good. There's one other thing that we know and that we can apply, and it's based on the statement earlier, and they do reiterate it up here, is that the belt speed we try to achieve somewhere between 4,000 and 5,000 feet per minute. So we're gonna list that as VB is going to be approximately 4,000 to 5,000 feet per minute. Okay, that'll be one of the things that we can apply. Now, the things that we have to find, what do we have to find here? Okay, so what variable is that? D1 and D2, right? We need to find D1 and we need to find D2. And we need to find what? And what is L? The length of the belt. And what is C? Center distance is C. And there's one more thing we're gonna have to find. The belt size, exactly. And that's really gonna be the kind of the first thing. So I'm gonna list that like up here, belt size. Okay. Because we can't determine the standard diameters until we know the belt size. All right. And I think that's what I have on my list. So I think we've got everything covered. Did anybody write anything else? Okay. All right. So the first step we need to do before we can do these diameters, these diameters have to come off of our commercial list. And if we go back to page 303, this is the commercial available shivs. We can't pick one of these values until we know which column we're going to be in. Okay. So we're going to turn the page, and to determine the size of the belt, we're going to use this chart. Okay. So step number 1 is going to be the size of the belt. And as you can see here, we're going to need to know the horsepower and the RPM of the faster shaft. So what numbers are we going to use here? What's the horsepower that we're going to use? 50, right? And then what's the RPMs that we're going to use? Nope, this is RPM. So we have to go off of, if you look here, this is RPMs of the faster shaft. So it's going to be one of our W numbers. Yep, the 1720 or 1725 RPMs. Okay, 1725 RPMs. So if you find where the 50 is and it intersects with 1725, what's the belt size that it lands in? Lex is saying 5V. Is that right? So here's 50. And here is 1750 or 1725, a little bit lower. So right about here-ish, right? So do you guys agree? Is it 5V? All right. So belt size equals 5V. And this is from, I'm sorry, figure 11.4. Okay. So this is one of our answers. So we can say that one is done. Step number 2. Step number 2. Now, step number 2 is going to be, now that we know what our belt size is, we have to pick our diameters, and we have to pick them to be commercially available. Okay. Now, we also know that our pitch line speed or our belt speed needs to be between 4,000 and 5,000 feet per minute. Okay. So to determine one of the diameters using this condition and our angular velocity, we can use that belt speed is equal to diameter divided by 2, this is our radius, times W1. Okay, so this is going to be off of our motor. All right. Now we know what our belt speed is going to be. We have a range, so we'll pick a number from there. We also know what the angular velocity is of our motor. But in this equation, can we use RPMs? No. Okay. And we have to think ahead here. This is the one where our belt velocity or our belt, I'm sorry, the velocity of our belt is going to be in units of feet per minute. And our W is in revolutions per minute. So when we convert that into radians, we can leave it in radians per minute like we did earlier. Okay. So let's use what we have here to then solve for D1. So rearrange this equation to solve for D1. So D1 is equal to, you can go ahead and do that and then we'll compare in just a second. Hopefully you got 2 times velocity of B divided by the angular velocity 1, right? Now, our belt speed. Our belt speed has to be within a range of 4,000 to 5,000. In the book, they just picked the middle value, 4,500, okay? So we're going to use that here. So this is going to be equal to 2 times, okay? And we're going to put 4,500 feet per minute, okay, on top. And then underneath, we need to do our W1, but we can't leave it in revolutions per minute. We have to convert it to radians per minute. So I'm going to do that work. Oh, I'll do it over here. So I have 1725 revolutions per minute. And I need to get that into radians per minute because we have feet per minute over here. So 1 revolution, 2 pi radians, revolutions cancel. And my W1 looks like it's going to be 10,838.2. Does that sound right? That value? And I'm going to plug that in underneath here. So that's going to be 10,838.2 radians per minute. Okay. Now, units. Make sure you put your units in every phase of the problem. And you also do the cancellation. I don't want somebody to just put down here D1 and just put random units. Cancel out what cancels. So that means that our minutes top and bottom are going to cancel. Feet and radians do not cancel, but what are the final units for this diameter at this point? It's feet, right? Because it would be feet divided by radians. Radians magically disappear, okay, when they're multiplied or they're combined with something else or divided into something else. So what is your value that you get here for your diameter? 0.8304 feet, right? Now, if we look at our chart and we're going to pick out our diameter, good chance that it's not in feet, right? It is in inches. So we need to convert this to inches. So we know that 1 foot is equal to 12 inches, feet cancel. D1 should come out to be 9.96 inches. Is that right?
Yep.
Okay. Okay. Now we're going to go. This is the calculated value for the diameter. So we're going to look. We got 9.96 inches. We're going to see what is the closest, or maybe 9.96 is on here. I don't know. So we have, these are our values in the middle column that we can work with. And we have 9.7, and then we have 10.2. 9.96 is kind of in the middle there, right? So we could either do 9.7 or 10.2. We are going to pick 9.7. Okay, we're going to pick 9.7. And this is the discretion of the designer. Okay, this is the discretion of the designer. So we're going to say that our D1 is going to be equal to 9.7 inches. All right. And this is from table 11.1. All right. Doesn't mean you have to go up. It doesn't mean you have to go down. You just pick the one that you think, I'm going to use that one. All right. So that means that we have picked our D1. Okay. We picked our D1. So now we can go ahead and pick our D2. Okay. Our D2. So step number 3 then is going to be finding that D2. So we know a couple things here. We know that our input is the 1725 RPMs and that we want to achieve about 600 RPMs on our output, right? We know what our diameter, number 1, is. We just picked it, okay? So if we use the velocity ratio, we can say that W1 over W2 is equal to D2 over D1, right? We know D1, we just calculated it here. We know W1 from above, and we know what we want to try to achieve for W2. So our only unknown here is what will D2 be? So D2 is going to equal W1 times D1 divided by W2, right? So we know W1, this is just a ratio, so we can go back to the 1725 RPMs, okay, times the diameter that we just chose from our commercial. Don't use the 9.9. We want to use the one that we actually pulled from table 11.1. That's inches, divided by what we want to try to get really close to, which is going to be 600 RPMs. Top and bottom, our RPMs cancel. What do we end up with for D2? So 27.9. Very nice, very convenient. Look at the last number on our V-belt list. 27.9. Awesome. So that means this even matches table 11.1. Now, chances are it's not going to be exact every time. So then you go with, again, you look at the closest one, okay? All right, so that means that we have D2 picked out, okay? This is good, this is good. So now what do we need to do? We need to do our length and our center distance, okay? So let's look at the equation for the overall length of the belt. The overall length of the belt, okay? Here's the equation on page 304. It's equation 11.1. And notice that in this equation, we know D1 and D2, but we don't know the center distance, okay? Remember, we were given the range of the center distance directly above here. The center distance has to be between, I should say, it has to be greater than the pitch diameter of the output sheave. And it has to be less than 3 times adding those two pitch diameters together, okay? So let's find the range that we're in, okay? So step number 4 is going to be picking our center distance, okay? So we know that D2 to center distance, and that has to be less than 3 times D1 plus D2, okay? So for these values, we calculated, or we determined our D2. We know that this is going to be 27.9 inches, right? And our C has to be between there. And then this has to be 3 times 27.9 plus, was it 9.7? Yes, yes. And what do you get for the value on this side? You have to speak louder, whoever is saying it. I don't know, somewhere in the back row. 112.8. What are the units? Inches, exactly. Okay. So this is the range that our center distance has to be in because they're not giving us one. So from the illustration, there is no center distance that we have to try to achieve here. Okay. In an application in the field, out in your workplaces, when you graduate, you're going to be standing and probably looking at it, or you're going to kind of know the space that it has to take up. You're going to have a better idea of what that is, but we get to choose between that. The book chose 72. Okay, they're like, we're going to start with a center distance of 72 so we can then specify a length. So we're going to say C is going to be equal to 72 inches. This is our trial center distance, not our actual yet. This is like a place we're starting, okay? So what that allows us to do is by using 72, we can then go back and calculate the length of our belt, okay? And see how close we are to something that's commercially available. So step number 5 is going to be L is equal to, and it's going to be, I'm going to use that equation down there. So it's going to be 2 times C plus pi over 2 times D2 plus D1 plus D2 minus D1 squared over 4 times C. Okay, so I just rewrote that equation right there. And that's what we're going to work with. So putting our numbers in place here, this is going to be 2 times 72 inches plus pi divided by 2 times 27.9 inches plus 9.7 inches plus 27.9 inches minus 9.7 inches squared. Don't forget to square that. Divided by 4 times 72 inches. Okay. So go and calculate your length. You guys get something right around 204.2 inches. Okay. So that's the amount of length of belt that we need to go over the top of these two shivs and maintain a center distance of 72 inches. Okay. Now, remember, it has to be commercially available. They don't make belts in every single size. So we need to now go to table 11.2 on page 305 and go to the 5V belt lengths, okay, right here. And we look, 204. I've got 200, I've got 212, I've got 190. 200 seems to be the closest, right? So our actual length, okay, length actual is going to be 200 inches, okay? This is a box, and this is going to be from table 11.2. So we use the center distance. We picked a center distance to just kind of, this is about where we want it to be, okay? So if we want it right about there, what's the length that I need? So this was kind of like a trial length, and now we compared it back to what's commercially available, okay? All right. Now, since we picked our actual length of the belt and we know exactly what our diameters are, number 6 is going to be, we're going to calculate the actual center distance, okay? So our actual center distance is going to be using equation 11.2 and 11.3. Notice that our B's that are in this equation, they are from this value down here. So what we do is we calculate our B based on our length and our pitch diameters. And then we use that B in the equation for the center distance, okay? So we have to calculate B first using the actual length, okay? So we're going to use actual length here. So we're going to do B is equal to, and that is 4L minus 2 pi times D2 plus D1. So again, that's that same equation. And now we're going to use our actual length here, not the 204. We're going to use the 200. This is going to be 4 times 200 inches minus 2 times pi times 27.9 plus 9 inches and inches. Okay. Don't forget your units. So B should get something relatively close to 563.8 inches. Confirmed in the room. Okay. Now this is not a final answer where this is kind of like on the way to. Now we're going to use that B in the actual center distance. Okay. Based on this length and the B. So this is the equation for that. I'm going to write mine down below here. Actual C is going to be equal to B plus square root of B squared minus 32 times D2 minus D1 squared under the radical, and all of that divided by 16. Okay. So that's going to be 563.8 plus square root of. Don't forget to put your units and everything. You should get a center distance 67.87 inches. Anybody get that or something very close? Make sure you're taking the square roots and the squares. Try again. It's 67.87, I know is right. Okay, do it a third time. Anybody else get that number? Josh, are you done with it? Did you get that? You're working on it. Okay. Isaac? 69.88, 69.88. Really? Just did it last hour. I gotta do mine again. Looks like Lex got 69.88 as well. So you guys are probably right. 563.8. Okay, 69.88. I'm gonna change mine to be that, as long as your numbers are the same as mine, right? Okay. All right. So it's not exactly 72 like we chose before, but remember, we chose that 72 to kind of ballpark to then determine what our length would be so that we could pick an actual belt length that was on our chart for commercially produced. And now using that value over the shivs, this is our actual center distance then, almost 70 inches. Okay. And then you as a designer would be like, is that okay? All right, and you would confirm that. And that also still is within the range of 27.9 to 112, you know, so it's nice and close, or it's nice and close to the 72, but in there, in that range still. So that means that if we look back at what we had left, we did find our actual length and we found what the final center distance was. So it looks like we found all 5 items. So make sure you have a box around identifying each one, showing the process, equations in variable form, units in all phases of the problem, and that I can read it. And we should be good. So any questions on this example at all? 11-2. All right. So if not, that brings us to the end of what I wanted to cover tonight. Okay. Now, this allows you though to get make progress on assignment number 6. Okay. So assignment number 6, we look to the end of our chapter here. The problems that are going to apply to what we did tonight are going to be the first 4 problems. So 11-2, 11-6, okay, 11-8. Now in 11-8, they want you to calculate the angle of contact over the smaller shift. We didn't do that in our examples tonight, but there are 2 equations, theta 1 and theta 2, that refer to this illustration over here. These are the angle of contact. I'm confident that you can do those. Okay. So I'm adding those in. So don't not do those, even though we didn't do them as part of our examples. You have what you need to do that with the equations. And then you'll also be able to do 11-12. Okay. The next time we meet, we are going to then be looking at the last half of this chapter, which is going to be gears. And then we have one more example problem to do, and then you'll be able to finish up the homework as well. All right. So, so that's where we're going to stop this evening. I'm going to stop the recording here.